output 1. If it is greater than this m, you can output 0. Is it okay? So basically for each a comma b, you will require only the m. So all that is left to do is compute this m, which you can do in the way that I have told. F of a comma b is, if s1 of a equal to s2 of b, then it is equal to 1 plus f of a plus 1 comma b plus 1. Otherwise s1 of a is not equal to s2 of b, so the longest common subword for that will be 0. So it is equal to, if s1, okay, that's a ternary operator used there. So that means if s1 of a is s2 of b, then f of a comma b is 1 plus f of a plus 1 comma b plus 1. Else if s1 of a not equal to s2 of b, it's equal to 0. Is it okay? Okay, how will you code this? F of, assume the first array is of size m and the second array is of size n. F of m of all j will be equal to 0. I mean, it is after, that is the first array is basically doesn't have any elements, so f of m of j will be equal to 0. And similarly f of I of n will also be equal to 0. Are these two okay? These two conditions? Yeah? Okay. And so for I is from m minus 1 to 0, for j is from m minus 1 to 0, that statement basically. Okay, for a is from m minus 1 to 0, for b is from n minus 1 to 0, just replace the parentheses by square brackets. F a b equal to s1 of a equal to s2 of b question mark 1 plus this statement here. That's all is the code for this problem. So what's the complexity? Yeah, it is n square or m into n if the sizes are m and n. The next topic I'm going to cover is, okay, first using memoization to avoid unreachable states. So first, what is memoization? Okay, so the technique we followed now, the code that we just wrote now is called a bottom-up way of coding this problem, because we already know the values of the states that we are going to reach now. Say, see, f a b, okay, if something f a b equal to 1 plus f a plus 1 b plus 1, right? Here we are assuming we know the value of f a plus 1 b plus 1 already. That is, we have already computed this value. So from some state we only go to the states which we have already computed. So this is called as a bottom-up way of going. Memoization is a top-down way of going. What that means is, if you are at some state, the state which depend on this, you may or may not computed the answer already for that. So for example, this same recursive this same code, this iterate, that memoization usually uses recursion. So this code, if I directly convert it to a memoization code, so I will also be writing the memoization template. Please follow the template. So you will have a int mem of say 100 of 100. So in the calling point, just initialize all the values of mem to -1. So I mean, there is a function called memset in C++. Memset mem comma -1 comma size of mem. Okay, so this will basically initialize all the values in mem to -1. So okay, the recursive code will go like int f, int a, comma int b. So first we will check whether we have already reached the state a comma b. this can be checked whether if mem of a comma b is -1, then this is the first time we are reaching this state. Else we have that means we have already reached this state before. So have this as a template. Int ampersand some ret equal to mem of a of b. So yeah, first you will have to check the conditions if boundary case, like if a equal to m, return 0, if b equal to n, return 0. So suppose you have those two lines before. So basically a memorization will look like base cases and then something like the data type ampersand ret equal to the value of this, the value mem of a of b. If ret not equal to -1, return ret. That means I have already come to the state before. So if ret not equal -1, return ret, and then just assign ret equal to so if s1 of a double equal to s2 of b, ret equal to 1 plus f of a plus 1 comma b plus 1, else ret is 0 and return ret. So the only thing which is missing in this code is the base case, which if a double equal to m or b double equal to n, return 0. So this is the code for memorization. Are everyone clear why this code works? I mean, is there any doubt? I mean, this computes this is also order mn solution only. This won't take any exponential solution, because for each state I store the value of that state also. So I don't need to compute this again in the next iteration. So this is the memorization. The thing to note here is, any state which you are in, you will have to compute. I mean, you won't be computing the values of some unnecessary states. All the states that you reach, the value of them you will compute for sure. But in DP you cannot ensure that. You will compute for some, you will also have to be computing for some unnecessary states in some cases. So that's what this slide talks about, using memorization to avoid unreachable states. So sometimes the state characterizations can only be very broad. I mean, you don't know which states you won't visit at the beginning, but in memorization you will automatically take care of that. So but actual number of states reached is very less, and so memorization looks only at reachable states. So this is one useful technique, but be cautious. Since this uses recursion, this is slightly slower if all the states are visited. I mean, if a majority of states are visited, you can go for bottom up. This is more faster than that. But if there are some unreachable states, then this is much faster. So one problem to practice is marbles on top coder. Okay, another important trick is space optimizations in dynamic programming. Note that this is only applicable in bottom up solutions and not top down solutions. I'll explain why later. So consider that you have to compute Stirling that is, just consider the recurrence f of n comma k equal to f n minus n k minus 1 plus k into f n minus n k. You can see that f of n depends only on f of n minus 1 comma something. So all the values you store, like n minus 2, n minus 3 and so on, are waste because you don't need them. For n you need only n minus 1, so you are wasting memory storing n minus 2, n minus 3 and so on. So you need only 2 arrays basically. So you can store the values using f of n mod 2 comma k. I mean, so if n mod 2 is 1 means then you have to access 0, and if it's 0 you have to access 1, or it is just your convention, I mean. So if you look even in this LCS problem, f of a depends only on f of a plus 1 comma something. So all you need to do is, for a you don't need the value of a plus 2, a plus 3 and so on. So at any point of time you need to store only two arrays. So okay, I'll implement this same solution using only 2 arrays. So okay, so the new type will be int f of 2 of whatever 2 of 100. First is this initialization. So f of m mod 2 of j equal to f of I mod 2 of n equal to 0, and that is for all j and for all I, that just look through it. And then for a is from m minus 1 to 0, for b is from n minus 1 to 0, if something f of a mod 2 of b equal to 1 plus f of a plus 1 mod 2 of b, else f of a mod 2 of b equal to 0. Is this okay? I mean, all you have to do is whenever you access the first index, just put a mod 2 there and it must work. So the answer is f of 0 of whatever. Is it okay? This is a special case in which one row is enough, but generally for say that one row, yeah, that also one row will be enough, but yeah, the complexity, the space complexity is the same, k and 2k. Correct. Okay, so just look at this problem. F of x equal to sum of f of a for all a such that a power y equal to x.
That is, like suppose if you are computing for f of 16, the value will depend, we need only f of 4 now.
And f of 2.
F of 2 also. So if we know the computation for f of 4, we just have to add the f of 16 to it and we can find the value. So basically what we are doing, we have to check only the roots of it, right?
Yeah, how will you find the roots?
F of 16, specificarity of f of 16 will give us f of
I mean, it can even be 27, right? For 27 you have to account for 3, right?
Oh.
You change the value of y from...
One sec.
Get the value of y from say 1 to 32.
Okay. Yeah.
And for each value of y, you calculate the corresponding value of a. For each value, I mean, you have to find f of x, right?
Yeah.
A upon y is equal to x. Assume that you have the x value.
Okay. Yeah, you have an x, yeah.
You have x value. So I vary y from 1 to 32.
Okay.
And for each value of y, I calculate
Power of x comma that. Yeah, we'll come later to the solution. Okay, first I'll tell the naive solution and then again ask you the solution I am expecting as naive, that is. So for each x, the problem is just that you have to find all possible a's such that a power y equal to x, correct? So for each x, look through all a and check whether for this a there exists a y such that a power y equal to x. So what is the complexity of this? For each x, there are n possible x. Inside that you have to do for each a, n possible a, checking whether a is a solution or not is order log n. So this becomes f of n, this becomes order n square log n.
You've calculated all the values till f of I.
F of?
Till some number say I. You just need to calculate, just need to add the values and find to I squared, I cubed.
Correct.
Till n. And then,
So what is the complexity?
n log n.
All you have to do is, when you are at a, add this value of f of a to a square, a cube, a power 4 and so on. So, so this is for each a, you will take only log n time. Because when you arrive at a itself, f of a would have already been computed. Because for the previous values also you would have updated like this. So when you are at a, update the values of a square, a cube, a power 4 so on. You will be using at most log n values. So it is an n log n solution. So this, in mathematical terms, why were we suffering, that is with the n square log n solution instead of this n log n solution? Because this is an example of a computationally tough inverse problem but an easy forward function. The forward function is just a to a square to a cube to so on, which is very easy. But the inverse function is factorization.